As you see the screen.
Yes.
Okay, hello everyone and welcome to
Yes.
session 4 of the swimming pool design course. So far we completed the 3 sessions already, and if we go back in a quick recap about the key points that we discussed in the last session, we spoke about how to do hydraulic calculation, like how to set the circulation pumps in terms of flow and head, also the horsepower and the kilowatt. Also, we spoke about the different types of filters and how to size them. We spoke about the backwash tanks and how to size it. We spoke about the skimmers and the different types of skimming systems, whether traditional or robotics. We learned also how to size all different piping works for supply and return pipes in the swimming pool, and many more actually that we can check them in the recorded video that I sent it to you. Everything uploaded already in the career learning portal. Okay. So in today's session, we are going to continue learn about how to do sizing calculation for all major items in the swimming pools. Okay. And I will do my best to complete this session, actually, the complete 1 hour. Ramadan Kareem, everybody, but it is difficult to keep talking 1 hour while I'm fasting. I will do my best. Otherwise, we can make it like a small session, divided this today and the next week. Okay, let's start. So as usual, the agenda is our main reference to see how we are progressing on this course. So today's topic is continuation for the swimming pool circulation system. I have extended here one more session because I found the content is too much and need more sessions actually. So I've added this session, and maybe I will add more if we divide it to small sessions. Let's see today if I can continue or not. Okay. Last time we discussed the piping, and we should jump to the next one, which is the sterilization system. Okay. Okay. So water quality, as we discussed in the first session, if you remember, it can be impacted by many contaminants, and we need to understand them in order to act with them accordingly. So we have biological contaminants, which are usually introduced by humans, animals, and the surrounded environment. We have like body fluids, sweating, and urines, too much urines, and we are going to see in the next video, vomiting, blood, and such human like waste, skin and the hair, also animals like birds, insects, or that pets that accidentally enter the pool, pathogens. Okay, we are referring here to the harmful microorganisms like viruses from human or animal waste. We have also physical contaminants like debris from the surrounding environment, such as leaves, grass, sand, gravel, dust and rust from pool equipment or the corroded fittings. Also, we have airborne contaminants. All of those contaminants impacting the pool water quality. So we need to understand them. So let's see if what we think of the chlorine smell in the pools is really from the chlorine or something else. In this video, the speaker does a cool experiment. He takes 2 buckets of fresh water, as we see here. He added chlorine to both of them, but one of them he added just a little bit of urine. Okay, so he closed them and then come back after 3 days. Okay, the bucket without urine, bucket A, does not have any smell. But guess what? The bucket having urine, which is bucket B, okay, smells just like a swimming pool, the common smell that we smell it in the pool. That's because the pee or the urine reacts with chlorine and creates like byproducts, which is what actually makes that strongest pool smell that we usually smell it. Okay. Scientists also found that all types of public pools having a lot of urine in the pool, in the water, from children and even adults, unfortunately. Sports Olympic pools are even worse because You see, this is the amount of pool that really we have in different size of pools. So as I said, the Olympic pools are even worse because the professional swimmers not going to the toilets while training to save time, and because they know the filtration system will handle this. So everybody relying on us guys. We need to do proper filtration for this. Uh, there are many disinfection systems, okay, but chlorine is the main disinfectant in pools. Even if we have ultraviolet or ozone or any other type of disinfections, still we have to dose chlorine for complete sterilization. And there are two common types of chlorine. We have gas and we have liquid. Both of them actually dissolves in the water, creating something called hypochlorous. This one, okay, HOCI. It creates hypochlorous acid. Okay. Uh, so to understand what happened to chlorine during the disinfections, let's break it down into three phases as we see in the screen. Okay, the phase one, when we put the chlorine, before disinfection, when we add the chlorine uh, to the pool, okay, it dissolves and just 1 second. It dissolve and release the hypochlorous acid. The, let's call it free chlorine, no, because it is difficult to say the chemical part. It releases the free chlorine, which is the most effective disinfectant that kills all harmful bacteria, viruses, and microorganisms. So this is the main one killing the the viruses. Okay, the free chlorine or hypochlorous. Okay, then in phase two, the reaction, the process itself, the disinfection process. In this phase, chlorine, the free chlorines interacts with the contaminants. Okay, the free chlorine attacks bacteria, viruses, and organic matter. Okay, and once it reacts, it is used up and no more or no longer available in the water. Okay, because some chlorine reacts with ammonia coming from the sweating or urine, as we saw in the video, to form something called combined chlorine. So we have second term now, free chlorine and the combined chlorine, and cause that strong chlorine odor in the pool. Okay, as we saw in the video. Some other chlorines break down due to sunlight. We call it ultraviolet degradation. Okay, because ultraviolet rays destroy up to around 50% of free chlorine within 1 hour if we don't have stabilizer in the water. So that's why we put stabilizer acid usually in the outdoor pools to prevent chlorine loss, to hold the chlorine in the water. Okay. So this was phase two. Then we have the last phase, which is called residual chlorine. Okay. Residual chlorine is after the disinfection reaction finish, the chlorine that remains in the water is called residual chlorine, or we call it total chlorine because it is like the summation of free chlorine and the combined chlorine. The free chlorine, the one that still not reacted, and the combined chlorine. So we have three terms now, and we need to understand them: free chlorine, okay, combined chlorine, and residual chlorine. The free chlorine, the amount of chlorine that is still available in the water to disinfect the water. Okay, this is the one actively keep killing bacteria, viruses, and other harmful microorganisms. Okay, which is the most important form of chlorine that keep the water sanitized. Okay, then we have the combined chlorine, the chlorine that has already reacted with the organic matter like sweating, urine, and other contaminants, but is still present in the water. So it will remain in the water, okay? And still also keep disinfecting, but it is very weak. It is not like free chlorine. It keep like making disinfection, okay? And this is the one causing unpleasant odor or the chlorine smell that we usually smell when we go to the swimming pool. So when you go to any public pool and you smell this chlorine, which means too much urine in the water, okay? And the residual chlorine or total chlorine, it is like the combination because it include free chlorine and combined chlorine. I hope you are not confused with me. Huh? So I've tried to do my best here in this flow chart to simplify this phases or this process, okay, to show the chlorine reactions until we reach to the residual chlorine that I explained to you. Okay, so we have the chlorine we added in the water of the pool. It produced the most important form, which is hypochlorous, or we call it free chlorine. And this free chlorine, some of them remain awaiting contaminants to come to react, and some other react already causing the combined chlorine. Okay, and both of them called residual chlorine. Okay, so we have here in this table uh, like comparison between the different types of chlorine. Okay, we have three types of chlorine, each one of them having like advantages and disadvantages. First, the chlorine gas. This one is cost effective, low cost. It doesn't cost too much, but require high safety precautions because the chlorine gas is highly toxic when inhaled and can be also fatal at high concentrations. So therefore, proper ventilation must be provided while we do the design for such type of chlorination when we use gas cylinders or stuff like that. And the second type called sodium hypochlorite, okay, which is a liquid phase. We call it liquid chlorine, the yellow one that if someone go to plant room, he can find it in big tanks, which is referred to uh, the issue with this one or the disadvantage of this one, it keep degrading over time. So if we have big amount, if we purchase big amount and they keep it long time with us, it keep degrading over the time and become not effective if we are not consuming this one. So this is one of the disadvantages of the liquid chlorine, and it needs space also because we have big tanks. And more expensive because we purchase this one from vendors outside. It is like ready-made liquid chlorine. We call it sodium hypochlorite. We need to remember this sodium hypochlorite. And the third type called electrochlorinations. Okay, so this provide a sustainable solution actually, but requires additional space. Okay, we need infrastructure for this one, as I'm going to show in details in the upcoming slide. So out of those three, the best choice depends on the project requirements. But myself, I like the electrochlorination system because it is much more efficient than the other traditional chlorination system. Uh, and as I'm going to explain the next slide better. Okay, so this is the electrochlorination system. Okay, this system is on-site chlorine production system because it generate sodium hypochlorite on site. We create this one on site. This system use only salt, regular salt, the food salt that we use it in our home, and water and electricity to generate the liquid chlorine. Okay, so no need for the regular chlorine storage if we use this system. And as you see here, we are using salt, water, and electricity, which is very cheap resources. That's why I like it. But it has initial cost to create this one. So how it works? First, we have to do salt dissolution. We put the salt. The chemical name of the salt is sodium chloride. We put the salt and they mix it with the water to create a brine solution. Okay, and then the next phase it's called electrolyze process. We the brine that we created in the first stage, we pass it through an electrolytic cell where like electric current breaks down the salt solution to produce the sodium hypochlorite, the liquid chlorine, sodium hypochlorite. So by using electricity and the salt solution, we can generate this sodium hypochlorite, the liquid chlorine that we are looking for. And then the last stage, storage and dosing. The generated sodium hypochlorite, we store it and then automatically dose them into the swimming pool as needed. Okay, so in this table, we show comparison with the other traditional chlorination. If we compare it to the liquid chlorine, for example, The electrochlorination system provide more stable and more effective solution uh, alternative to buying commercial sodium hypochlorite, as I just explained. So instead of keep buying material from vendors, I am generating this in my home. I mean on site. Okay. If we compare it to the gas one, it is much safer than handling hazardous chlorine gas cylinder on site. So it is much better. Also, if we compare it to the calcium hypochlorite, the very traditional one, the solid tablets, if someone of you saw some people using solid tablets on the swimming pool, so still the electrochlorination like much better because it's eliminate the calcium residue build up that we usually found when we use the calcium hypochlorite, the solid tablets. Okay, so no need for frequent manual dosing if we are using the solid tablet. In this video, okay, explain how the system works. In the initial start, we have to prepare the system. You see here, he put salt in the tank. Okay, this is called the brine tank, and provide fresh water to all pipes, including the brine tank. Okay, so then the salt should be mixed properly with the water to create the brine solution. See here. Then we have brine. We mix the salt with the water. We have brine. The brine is passed through an electrolytic cell, as we are going to see here, to generate the liquid chlorine, sodium hypochlorite. See here. And then here, the electrical current breaks down the salt solution to produce the sodium hypochlorite, as I just explained. This is the liquid chlorine. The system in the video here, this yellow one, this is the liquid chlorine. Okay, in this video, the system in this video, they are using 3 tanks, but actually the third one is not required. It is just optional. They provided this fan to release the hydrogen because one of the chemical reactions, the results of the chemical reaction, hydrogen. So we have to vent it to take it out through flower. Okay, so the third tank, as I just said, it is optional. It is not required in this specific example. He provided to like just to provide auto cleaning for the electrical rods. You see here the scale for forming around the rods. It impacted the efficiency of this one. So every month or every 2 weeks, automatically the system take the chemicals from the tank to clean it, and they return it back again to ensure the system is efficient all the time. Okay, so it could be 2 or 3 tanks or whatever. Yeah. So this is the system. You see it needs a space. Okay, so this company, for example, they offer to provide in a container for to treat it as a separate system. Okay, like closed box. Okay, in order to do sizing for electrochlorination system, we need to determine the chlorine demand of the pool. This is the main target. So we need also to ensure the system can generate enough sodium hypochlorite to meet this demand. So we calculate the demand and to calculate the sodium hypochlorite that meet this demand. Okay, so to calculate the demand, first we have to know the volume of the pool. Okay, this is the first step, and then the next step we should calculate the dose per day, depending on the demand value of my pool as listed in the screen, which is vary from 2 up to 10 gram per cubic meter per day. So depending on the load that you have, you can select the suitable value suit your pool. Here in step 3, we should convert the chlorine dose calculated in step 2 to sodium hypochlorite. Okay, the one that we need to generate by our system. Okay, so concentration of sodium hypochlorite in these systems ranges from 0.6 to 0.8 percentage, or we call it 6 to 8 grams per liter. Let's use 7 gram per liter. So if we divided the calculated chlorine dose per day by the recommended concentration here, we'll get the amount of sodium hypochlorite that needs to be produced by our system. So then in step 4, we have to estimate the amount of salt, because this salt produce the sodium hypochlorite. We have to calculate it as well. So in step 4, we have to estimate the amount of salt needed to produce the calculated sodium hypochlorite in step 3. Okay. So to generate 1 kg of chlorine, the liquid chlorine, I mean the sodium hypochlorite, we need 3 to 4 kilograms salt. So every 1 kg liquid chlorine, we have to consider 4 or 3 kg salt for this one. Okay. Once we calculated everything, we should consider also some buffer as a factor of safety, around 20 or 30% to ensure we always save. So let's practice here in our famous example that we always use it. If you remember this pool from the previous sessions. Guys, you have any questions? You are with us? Okay. So first we have the pool volume calculated, 300 cubic meter. We calculated many times before. Then we calculate the dose per day, depending on the demand value of my pool as listed previously. Okay. So for public pools, it needs from 8 to 10 gram per cubic meter per day. So if we use 8, we will get the dose by multiplying with the pool volume. See, we got here 2,400 grams per day. Okay. Then in step 3, we need to calculate the amount of chlorine to be generated. Okay, the sodium hypochlorite that we need to generate. So as we said, the recommended concentration should be 7 grams per liter, if you remember. So we can get the chlorine amount by dividing the daily dose by 7. It gives me 343 liter per day. Then the same in step 4, we got the salt consumption by multiplying 3.5 kilogram, the recommended consumption, into 2.4 gram, the calculated daily dose in step 4, if you remember. So the last thing here, we should size also the flow of dosing pump by using the given data in our example. If you remember, we have calculated the pool flow rate before in the previous sessions, 75.6 meter cube per hour. Okay, and we know also the recommended free chlorine level between 1 to 3 ppm. So we will use 2, for example, in between. And we know also the concentration of sodium hypochlorite, 0.7 or 7 gram, 0.7% or 7 gram, okay, grams. So substitute all of this information in the formula to get 21.6 liter per hour, as you can see here in the screen. So the dosing rate of the pump, 21.6 liter per hour. Regarding to the head of the pump, it depends on the system back pressure, which needs to be slightly higher to dose the flow. So let's say if you have 2 or 3 bar, the system pressure, you can make it slightly higher, around 0.7 bar or maybe 1 bar, because you need to overcome this back pressure coming from the system. So you have the flow and the pressure. Now the dosing pump calculated. Okay. One of the main factors that we need to keep tracking also, the pH level, hydrogen index, the pH level in the pool water, okay? Because any imbalance or disorder in the pH, we will face many issues, as we discussed in detail in the first session. If you remember, if you go back to the first session, I show you what are the different scenarios happening when you have high pH or low pH, and the pool water color changing based on the pH level, and what were the reasons happening due to this disorder in the pH. So the pH is very important. So this pH level measures how acidic or basic the water is. Okay, as we see the scale ranging here from 0 to 14, which plays a crucial role in your pool chlorine effectiveness. Okay, which is normally decreased if we have high pH levels. So 7 which means neutral. If we have 7 pH, which means neutral, below 7 acidic, okay, higher than 7 alkaline, okay. So this is the scale range of the pH. So maintaining the pH level in the swimming pool is crucial for water quality. The ideal pH range for a swimming pool is 7.2 to 7.8. And if we make it 7.4 to 7.6, it will be much better. Okay. And there are different ways to maintain the correct pH levels, as we discussed before. First, we can adjusting the pH level. If we have pH too high, higher than 7.8, we can add something called pH reducer, acidic component, such as sodium bisulfate. Okay, if the pH is too low, lower than 7.2, we can add pH increaser, alkaline compound, such as sodium carbonate or soda ash. Okay, also we can maintain the pH level by maintaining the alkalinity within the range. There is range for alkalinity also. It needs to be maintained between 80 to 120 ppm. If alkalinity is too low, we can add sodium bicarbonate, or we call it baking soda. If the alkalinity is too high, we can add acid like muriatic acid in a small amount because it is very powerful. So we can play with the pH level by adding different chemicals to adjust the pH within the required range. This is the point that I want to explain to you. No questions, huh? Okay. So to maintain the pH levels, we need to use pH corrector to adjust and keep the water pH levels within 7.2 to 7.6, as I just said. Okay. So with the help of chemical dosing system, we can maintain this one. As we see in the screen here, the key components of the pH control system, I listed them down with some pictures to make it clear for you what are the key components of the pH control system. So the first one, pH sensor and the controller, okay, which include pH probe, continuously measures the pool water pH level, okay, and then the controller compares the pH value to the set point. As we said, it should be between 7.2 to 7.6. If the pH deviates, the controllers send a signal to the dosing pump in order to start dose as needed. If it is, it depends, it's acid or base required based on the result. So this is the first one. The second one, the dosing pump, we use it to inject acid or base into the pool water. So we need to choose a pump with adjustable flow rate type because we are dealing here with a small and accurate flow rate. So it has to be adjustable flow type, okay? So there are two common types of dosing pumps as we see here in the screen. The first one is called peristaltic pumps. This one gives low flow and low pressure actually. So we use it usually for small pools because it is easier to maintain. And the second type of pump is called solenoid driven pumps, which is more accurate. It gives higher precision than the other one. And we use it normally for the high pressure system or large pools. Okay, so those are the common two dosing pump. The third item that we have here, the chemical storage tank. We use it to hold the acid or base solution to be dosed in the water, and this tank usually made of high density polyethylene to resist the chemical corrosion happening due to storing this material. Okay, and number 4, we have injection points or accessories. Actually, this is very important accessories in this system, because we use them to inject the acid or base into the return line of the circulation system after the filter, but before the return to the pool to ensure proper mixing before reaching the pool. Okay, and the last one we have here, flow sensor. This one we use it to prevent dosing the chemicals, okay, when the pool circulation is off. If the pump is off, we should not keep dosing. So this sensor, it help us to sense we have like flow or not, and accordingly it give signal to the dosing pump to stop or keep working. So this will help to enhance the safety and efficiency of the system. Those are the main components of the pH control system, and understanding the function of every one of them will help us to do proper design and piping connections. So in terms of connections, we need to also to consider also to place the sensor in the main return line after filtration, and to inject the acid or base, whatever needed, okay, to inject this in a high flow area, like return line downstream the booster pump or the circulation pump. Okay. So also we need to consider installing safety interlocks like flow switch to prevent dosing when pumps are off, and over feed protection also in the controller as well. So next one. As we just explained, we are using acid or base solutions, so reduce or increase the pH levels. It, it happen by using specific some chemical solutions. Okay, so we need to remember this. If we need to reduce the pH, we can use muriatic acid. If we need to reduce the pH, also we can reduce sodium bisulfate. If we need to increase the pH, we can use sodium carbonate. We call it soda ash. So for every action, we have single like chemical needs to be used in order to achieve the job. So understanding the recommended concentration of those chemicals will help us to estimate the demand that suit my pool, which is the first step in sizing the pH in those system. Okay. So as listed in the screen, if we use muriatic acid, for example, consider 1 liter per 50 cubic meter of water to reduce 0.2 pH. So if you want to reduce the pH uh, 0.2, okay, in the scale that I just showed you, we use 1 liter for every 50 cubic meter of the water bowl. If we, and the same for the sodium bisulfate, this is solid actually. So we measure it by kg, by kilogram. We consider 0.5 kg for such amount of water, and so on. So based on the recommendation here, we can size the needs in terms of chemical to achieve the pH adjustment. So once you estimate the demand, we do the same to select the dosing pump, because the dosing pump in the pH system is a little standardized, because we don't have continued dosing like the chlorine dosing, for instance. It's just feed as needed automatically to maintain the pH level. So you can roughly select dosing pump that suits your bowl, something between 1 to 10 liter per hour. Okay, as we will see in the next example. So here in this example, we have a small pool, like 100 cubic meter volume. So if we use the muriatic acid, we need 2 liter per hour dose to adjust the pH, as I just said, 0.2. So if the pH correction needs to be done within 2 hours, then a dosing pump with 1 liter per 1 hour is enough to do this job, okay? And so on. Let's see example here. Here is another example, our famous pool that we always use to practice. We know the volume of this pool, 300 cubic meter. If we divide it by 50 cubic meter, it gives me 6 liter per hour, okay? So it could be expanded for 2 hours for the pH correction. Therefore, 3 liter per hour is enough to do this job if we need to manage this within 2 hours, okay? Simple. Okay. This ozone disinfection system. We finish now the chlorination or the electro things, and the pH also. Now in commercial pools, we use ozone as an alternative solution to reduce the dependency on the chemicals. Additionally, it is more effective actually than chlorine alone. It kills all harmful microorganisms in the pool water. Okay. Uh, so what is the ozone disinfection? Ozone is powerful oxidizing agent. We use it as like alternative or supplement to the traditional chlorine disinfection in the swimming pools. Okay, it is like a gas composite of three oxygen atoms. That's why the symbol of this O3. Okay, and is known for its ability to kill bacteria, viruses, algae, and other organic contaminants more effectively than chlorine alone. Okay, so how does ozone work in the swimming pool? In this system, actually, ozone is generated on site using ozone generator. We are bringing generator on site to produce this ozone and then injecting this ozone to the pool water via Venturi injector, as I'm going to show you in the next slide. And also we use contact tank in order to make it properly react with each other. Okay, once dissolved in water, ozone acts very quickly and disinfect the water and kill everything. So as we see here in this table, we show what is the advantage and disadvantages of this system. So the benefit of ozone disinfection in the swimming pool, first, it doesn't cause skin or eye irritation like chlorine. Chlorine sometimes cause skin and eye irritation. In ozone, we don't have this. Okay, effectively removes odor and enhance water clarity. Unlike chlorine, if we have too much chlorine, it cause cloudy. It cause cloudy water, as I show you before in the first session. Okay, and this providing also strong disinfection by eliminating all bacteria and the viruses and all other pathogens that chlorine cannot remove it. And it doesn't produce harmful byproducts such as chloramine. You remember in the chlorine, the combined chlorine called chloramine, the one causing strong smell in the pool, the one that I show you in the video. Okay, so those are the benefits of the ozone. There are also some drawbacks of using ozone. It needs high initial cost, okay, because we are generating ozone on site. It needs cost, unlike the chlorine, it is just some tanks and pumps. It needs large plant room for installation. You need space to put the equipment. What else? And there is no residual. This is very important. This is one of the main drawbacks of ozone. No residual disinfectant effect with ozone. Ozone only react at the moment of reaction. Okay. After that, the water go doesn't have residual. Unlike the chlorine, the free chlorine react and cause combined chlorine, and the remaining will keep free until finding another contaminants in the water outside. Okay. We need to consider also one of the main drawbacks, extra dosing of ozone. It causes issues in terms of material corrosion because it is oxidizer. Okay, it causes material corrosion and also long-term exposure for the swimmers. It might cause health issues. That's why we should not keep any residual ozone in the water. Once the disinfection process happen in the plant room, it should be immediately removed or eliminated, as I'm going to show you now. Okay, so what are the components of the ozone generation system? First, we have something called air treatment unit. We call it absorber. Okay, this one removes moisture and dust from the air before entering the ozone generator unit to ensure efficient ozone production and also prevent unwanted byproducts. Okay, and then after that, we have the ozonator, the generator, ozone generator. Okay, this one convert the oxygen in the air provided by the absorber, convert the oxygen O2 into ozone O3, and produce high reactive ozone gas for disinfection. Okay. So this is the second one. The third one is mixing equipment. Okay. So in the mixing equipment, we ensure proper dissolution of ozone into the water. We use Venturi injectors. We have also static mixers to enhance the ozone transfer to the water. Okay. We have ozone analyzer. This is number 4. We monitor ozone concentration in water to maintain optimal levels and to ensure compliance with the health and safety standards. And number 5, we have reaction tank. This tank provides sufficient contact time. Okay, we around five minutes for ozone to react with the contaminants, and this allows oxidization of bacteria, virus, and organic pollutants. Okay. And the number 6 is carbon filter tank or vessel. Okay. This carbon filter, we use it to remove the residual ozone, as I told you, because it is harmful. We cannot leave it to go back to the pool again because it causes issues to the swimmers and also to the equipment. So we have to remove any residual ozone uh, before going back to the system again. Okay, so this prevent excess ozone exposure in the pool because, as I said, prolonged exposure to ozone causing damage to the lung tissues of the swimmers. Okay, here is another arrangement. Instead of using carbon filter, we can use mass transfer tank, which release the extra ozone automatically. But in this system, we have to add ozone destructor. Okay, this unit here. I have the pointer. Okay. We have to add the ozone destructor unit to break down the excess ozone before releasing to the atmosphere, because even we cannot release this ozone to the atmosphere. If we remove it from our system, we have to break it down. So how this system works? First, we need to, you see here from the picture, okay, we need the first thing to do the air preparation, as I just said. The air treatment unit in the right-hand side here, okay, dries and clean the air before entering the ozonator. Okay, and then next step, ozone generation. The ozonator convert oxygen in the dry air into ozone, and then the next step, ozone injection. Okay, in this stage, ozone is mixed with water using the Venturi injectors or diffusers, as we see here in this picture. Then the reaction phase. Okay, ozone disinfects the water in the reaction tank, okay, or the mass transfer tank. It depends which arrangement we are following, okay. And then finally, the residual ozone removal. We have to remove any excess ozone. Any excess ozone is removed via carbon filter or ozone destructor unit, like this in the picture, before the water returning to the pool to ensure compliance with the health and safety standards. Okay, so we need to note all, yeah, as I just said, the ozone is very strong oxidizer. So we need to consider all material with direct contact with ozone must be ozone resistant material. Okay, this is very important note. So how to size every component in ozone system? What is the time? Time is running very quickly. So how to size every component in ozone system? Guys, no picture, no questions? Ramadan Kareem, you still focus with me?
Yes.
Yes, yes.
طيب, okay.
Yeah.
So how to size every component in ozone system? The first one, the air treatment unit. Okay. So the absorber, how to do sizing for this one? The purpose of this unit to remove the moisture and containment from the air, as I just explained, before ozone generation to improve efficiency and prevent also damage to the generator. So the sizing factors of this unit, okay, is the airflow rate in cubic meter per hour. So in order to size this one, to go to the vendor and tell him I need to purchase this one, he will ask you what is the airflow required for this one. So based on the ozone generator capacity, we can size this air treatment unit. Okay. So as we need to consider 12 liter per minute air required to produce 1 grams per hour of ozone. So after sizing the generator, the ozone generator, we can size this absorber. I started by this one, but you will see in the next slide how to size the ozone generator. So every 1 gram of per hour of ozone, you need 12 liter per minute air. So according to this, you can calculate, you can size the absorber. Okay. So as we see in this example calculation, if we have 90 grams per hour generator, we need at least 65 cubic meter per hour absorber unit. Okay. Okay. So here we know the ozone generator sizing. Okay. So the ozone generator capacity depends on the flow rate and ozone dose required for effective oxidation and disinfection. Okay. So to size the generator, okay. So to size the generator, we need to apply the recommended dose, which is 1 milligrams per liter in the formula displayed in the screen. Okay, so we can set the ozone generator unit according to this formula. So as we see in this example calculation, if we have pool with flow rate around 100 cubic meter per hour, we need 120 grams per hour generator. Okay, simple, I believe, very straightforward. Then the Venturi injector. Okay, how to size this one? So the purpose of this Venturi injector is to create vacuum to draw the ozone gas into the water stream. So you know the concept of Bernoulli equation. If you increase the velocity, the pressure will drop down, create vacuum, and then sucking the gas and inserted inside the flow. The same concept of the spray of perfume. Okay. So regarding to selection guidelines, we choose injector that matches the pool flow rate and the delta P pressure, also the pressure differential of the system. Also, we need to ensure suction capacity matches the ozone gas flow. Okay. So the typical injector water flow rate around 20 to 25% of the whole pool circulation flow. So as we see in this example calculation, if we have a pool with flow rate around 100 cubic meter per hour, we choose a Venturi injector rated for 10 to 25 cubic meter per hour to achieve the 10 to 25 percent the selection guidelines, as I just said. Okay. Okay. Static mixer. So the purpose of this item, the static mixer, this mixer enhance ozone dissolution efficiency before entering the reaction tank to ensure uniform mixing of ozone with the water. So from the name, it's called static. You see the bubbles here. These bubbles, it creates like it's like steering the ozone inside the water to ensure it is properly mixed. So the key selection parameters here is the length of this mixer. So when you go to purchase this one, you tell the guy, I need this lens of mixer. So this lens is supposed to be like sized like that, 5 to 10 times the pipe diameter to give enough mixing time for ozone. Okay, so if we have like 50 mm diameter pipe, it means we need a mixer with length around 500 mm, as we see in this example. Okay. The reaction tank sizing. Okay, so the purpose of this reaction tanks allows ozone to oxidize the contaminants before water returning back to the pool to ensure sufficient contact time for ozone to react with the contaminants. We give it time or like slowing down the flow in order to ensure it is like in contact as long as possible. So the key selection parameters is the key selection parameter of this item, the contact time. So this one, it should be considered from 1 to 5 minutes to allow proper oxidization in the flow. Also, we need to consider the pool flow rate in meter cube per hour. So those are the two main parameters in order to do the selection. Okay. So as we see in this example calculation, if we have a pool with flow rate 100 cubic meter per hour, we need tank with 3.5 cubic meter capacity to achieve the recommended contact time that we consider here in this example, 2 minutes, right? So also some other considerations in this specific item, the material, it should be high density polyethylene because we need, as I told you, ozone resistance material. The ozone like staying here too much, so it has to be ozone resistant material, which is usually HDPE, the best one, or fiberglass or stainless steel or any similar ozone resistance material. So it's vertical as we see here, but inside it has like buffles to improve the retention time of this flow. So it's like buffers inside. Okay, degassing system. As I just explained, we have two types of things. Okay, to remove excess ozone gas from water before it returns to the pool, it could be done by activated carbon or thermal destruction unit to break ozone down into oxygen. So we are going to size both cases to ensure we cover all scenarios. Okay, so the first option we have here, the off gas destruct unit, the one that we use it with the uh, mass transfer tank, the one that we explained 2 slides back. So the purpose of this unit here, this one, the gas destruct unit, to remove excess ozone gas by converting to oxygen. So the O3 we convert it to O2, we return it to O2 back again. Okay. So in order to do so, they are using here catalytic or thermal destruction methods to like safely neutralize the ozone and they make it oxygen to release it back to the atmosphere. So sizing basis of this unit, capacity should match 100% of ozone injection flow rate. So whatever the capacity you have in the ozone injection, it has to be the same. Okay. For in this example calculation, if we have 100 grams per hour of ozone injected, okay, the destructor, the destruct unit should be sized to handle at least the same size, 100 grams per hour of gas removal. Okay. Okay, the second option of gas removal is carbon filter tank, the vessel. So the purpose of this one to neutralize residual ozone before returning to the water, to the pool, the same function, but here the ozone will be neutralized in the water, not in the air. So sizing basis of this one, the retention time, it should be from 5 to 10 minutes. And also the depth of material, it should not less than 600 mm, from 600 to 900 mm. Okay. So as we see in this example calculation, if we have pool with flow rate 100 cubic meter per hour, we need carbon filter tank with 20 cubic meter capacity. Okay. Okay, ozone mixing pump. So the purpose of this unit, it provides pressure in the venturi for ozone injection. Okay, it's like side stream pump. It takes from the flow and pushing, okay, and pushing to the flow to the venturi in order to mix it with ozone. So the sizing basis of this one, side stream rate, around 10 to 20% of the total flow of the system flow, total flow. And the pressure also should be around 1 bar higher than the system pressure. So two things, consider around 20% of the total flow, circulation flow, and the higher than the back pressure coming from the system around 1 bar. So as we see in this example calculation, if we have pool with flow rate 100 cubic meter per hour, we need around 15 cubic meter per hour side stream pump to handle the flow. Okay. So the residual disinfectant systems, chlorine or bromine, the purpose, this is it's supposed to be like one of the main things associated with the ozone system. Okay. So the purpose of this one to ensure secondary disinfection system provided to the system, because as I explained in the beginning that the ozone system is very effective in killing the harmful contaminants only at the time of reaction. Okay, only at this moment. But also, this ozone system unfortunately does not have residual disinfection to go back to the pool for continue protection to the water in the pool. Therefore, we have to use chlorine as a second disinfectant to provide that residual effect. Okay, so in this case, we have different calculation to size the chlorine comparing to what we did before, because we have here less demand and less concentration of chlorine at the system here secondary, not primary. So we just provide residual chlorine in order to just be ready for any contaminants coming inside the pool water. Okay, so the water out of the ozonization system go with almost zero contaminants, but maybe inside the basin of the pool, contaminants coming with the swimmers. In order to 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 keep sanitizing this one, we have to provide the residual chlor. So key sizing factor here for the dosing demand is like ranging from zero point 0.5 to 2 milligrams per liter, depending on the size of the pool, as listed here in the screen. Okay. So as we see here in this example calculation, if we have pool with flow rate 100 cubic meter per hour, we need around 80 grams per hour chlorine for this one. Okay, which is very minimal comparing to the previous chlorination dosing that we did it before. Okay, here we have another type of disinfection, which is called ultraviolet. Okay, so the ultraviolet radiation is water disinfection method that use high energy ultraviolet lights to inactive or destroy harmful microorganisms. Okay, it is like a chemical free process that enhance the water quality and reduce reliance on chlorine-based uh, disinfectants. Okay, so what is the working principle of ultraviolet system? In ultraviolet system here, typically installed in the swimming pool recirculation loop after the filtration system, as we see here in this diagram. The water passes through ultraviolet chamber, okay, and exposed to ultraviolet light. This process helps to neutralize harmful microorganisms and also improve the water quality. Okay, but also we have the same issue of the residual chlorine residual here. We need something to maintain residual disinfection. So although the ultraviolet disinfection kills bacteria and virus, it does not leave a residual disinfectant in the pool. So secondary sanitizers, such as the chlorination, still required to maintain long-term protection in the pool water. Okay. Okay. So this like ozone, okay, it has in order to size this one, to size the ultraviolet one, so we need to understand first what is the dose of ultraviolet. Okay, so the ultraviolet dose represents the amount of ultraviolet energy that microorganisms such as bacteria, viruses, and algae receive. Okay, and this is function of ultraviolet light intensity and the exposure type that we keep the water under the lighting. Okay, so a higher ultraviolet dose means a stronger disinfection and better inactivation of harmful microorganisms. Okay, so we can use this table as a reference to match the ultraviolet system capacity with the flow rate at the required dose that we need. Okay, so we should select an appropriate ultraviolet dose from 30 to 100 millijoules per square centimeter, mg per square meter. This one means millijoules per square centimeter. Okay. Okay. So from this table, you can set the ultraviolet system. Okay. So we finish now the sterilization system. If you just give me 10 minutes or 5 minutes maximum, we'll finish this one. I know we finished it is the 1 hour finished already. Just we need to speak about the heating load to finish the skimmer. And then the next session, it will be very short. So here, calculating the heating load for swimming pool involves actually several key factors like pool volume, the desired temperature to raise, the heat losses, and energy efficiency as well. So we will follow ASHRAE method to calculate the heating load for the swimming pool as we see here in the screen. So in order to do this estimation, you need to consider two heating load. Q1, okay, the heat required to raise the pool water to the desired temperature, which is the most important one. And let me just open this very quickly, laser. And Q2, the heat losses due to the evaporation from the pool. So we have Q1 here, m.Cp delta T, the famous one, but it's itemized to make it clear for everyone what is how to substitute in this formula. And here we have the heat losses due to evaporation, UA delta T. Okay, so if we go one by one here, we have the rho, the density of the water, which is 1000 as we know, and the Cp 4.2 kilojoule, and the volume of pool, okay, that we should be aware about it. And the delta T here is supposed to be between the desired temperature and the initial temperature, okay, when we put the water in the pool. And this theta, okay, the time required to heat the pool, it could be in 1 day, 2 days, 3 days, as you wish. So as more time, as less capacity that you have for the equipment. This is number one. And here Q2, the U, okay, the heat transfer coefficient, okay, between the water surface and the air, and the pool surface area, okay, and the delta T here between the pool temperature and the ambient air temperature around this one, because we have heat losses from the pool surface to the ambient air or the indoor air, whatever the design of this pool. So if we see here in this example, our famous example here, we have considered here the initial pool temperature 20, and we need to reach to 28. 28 is the optimum, like optimal one that we need to consider. Higher than this, it will be like you will feel not comfortable in the pool. And we consider here 24 hours as to heat up the pool, okay? And the ambient air temperature 15 degree in the winter, okay, and use this heat transfer coefficient 0.06. This we use it normally with medium air velocity to calculate the heat transfer due to evaporation, and the specific heat 4.2 we know, and the density 1000 kilogram per cubic meter. So by all this given data, we can calculate Q1, it gives me this, and we can calculate Q2, it gives me this. So the total, where is the total? This is the total, okay? This is the total heat required. By using this, we can bring whatever heat source to achieve this job. So it could be like a booster heater like this one, or it could be any other, like maybe it could be like gas burner, it could be a heat pump, okay? So the only difference in sizing when we have heat pump or heat exchanger, there is efficiency for such equipment because you do heat transfer. Consider this efficiency and increase the load based on the efficiency. For example, if you are using heat exchanger with 80% efficiency, so divide this one by zero point 0.8, it will give you around maybe 300 or something like that kilowatt. It will be slightly higher. If you have the heat pump, they're not using efficiency, they're using COP. So consider like 5 COP, which means high efficiency heat pump. Divide this by 5, it will give you less kilowatt, and so on. So, but this is the main one. Now we learned how to do the main one. Okay, so we finish now, and
Khalil, just one question. The pool heat up time
yeah,
represents what the number of hours you want to be heating the pool for, or what?
yeah. Okay, let's go back to, you are talking about this 24, huh?
Yes.
So this, which means you spend 24 hours to heat up this one to achieve the desired temperature. Okay, but I
Okay.
used 1 day as a reference as a unit. So once I get this number 116, this is the total kilowatt required to heat up within 1 day. You can make it 2 days. So divide 116 by 2, it will become like less 50%. You can make it by 3. So divide this one by 3 and so on. Yeah, normally we heat up the pool. I'm talking about the startup of heating pool from scratch. And you have the pool, you filled by water, too much cold. So you need to heat up this one from zero, not from zero, from the initial temperature, which is considered here 20 degree, up to 28. So it takes like 1 day, 2 days, 3 days, and so on.
Okay. But you
Okay.
can make it less, for example, if you need to heat the pool in few hours, then.
You can do whatever you want. If you have money, make it like 1 hour, but you have
Okay.
very big heater. Okay.
Mm.
So as more load, as more bigger size of unit you have, and the more expensive it costs you money. But I'm teaching you here the main thing. You need to calculate the heat load of the pool. So once you get it, you can do whatever you want. You can play with the figure. You can say, ah, this is too much. I need to make it smaller. So divide it by two, three. You can bring heat pump, so you can divide it more. If you divide this by 5 COB, it will give you very small unit, and so on. And even the heat pump itself, there are details in selecting the unit. The heat pump, it could be water cooled, air cooled. Okay, water cooled is more efficient, so and so on.
Okay.
Okay, so this is the main thing to calculate the to heat up the pool. Okay,
Okay. Thank you.
so guys, I hope I was
Uh,
clear.
Hi,
Uh,
Khalid. Just
hi,
one doubt regarding
Abdul.
the initial temperature. How come this is 20? Could you please explain on this?
Yeah, maybe it is wrong. Okay, if you have,
Because we are calculating, right? We know our desired temperature may be 28, like always 28 plus or minus 1, and we know the ambient condition. But how we are fixing this initial temperature as 20?
yeah, you can. There are many sources to get this temperature, Zubair. Like here in Dubai.
Hmm.
Okay, we have the Dubai recommendation. It could be used as a reference. Okay,
You
you
mean
know
to
the,
say that the filling water temperature is it?
yeah, the filling water temperature.
Okay,
That I'm
okay,
talking
got
about
it.
the raw water coming from the regular domestic
Okay,
water
okay,
tank. So I
okay.
have a project here, the source of water coming from Dubai municipality. So
Yeah,
I
the
know the
table.
temperature from the network around 20, maybe 18. Okay, in summer it become very hot, 44, 40. In winter, it is not going below 20, I'm sure. In my home, I have never used the electrical water heater at all. I'm taking shower with the cold water even in winter.
So it's
So
a winter condition if it is coming 20, but in a hot condition that temperature goes rise, right?
yeah, it goes rise. But remember, here I'm talking about the startup heating, starting from the initial temperature.
Initial. Okay.
But then over time, the heater job, it will be only to maintain the heat losses due to like conduction, convection, and the stuff like that. All heat transfer happening over time. So if you have internal pool, okay, guys, we need. It's a good question actually. You see here this equation, UA delta T. This one for the evaporation happening from the pool surface, right? So if we have indoor pool, Okay, and we control everything, all temperature, air temperature and the pool temperature. So usually the HVAC designers, if we have HVAC designer here with us, usually they do what they consider the air temperature in their design higher than, slightly higher than the pool temperature to minimize the condensation. So if we have the pool temperature 28, they do their calculation based on 29 or 28, but it is not lower than this because if it is lower, it keep evaporating, and over time you will find the whole room fill with
Fog.
condensation. Okay, so you can apply this here. For example, if we have indoor pool TI, which is the pool temperature 28, and uh, TO ambient temperature, which is 29 higher, which means negative. So in such cases, the heat losses due to evaporation, you can consider it zero here. So you will rely only on this one. So this is the way that you play with the figures. You know the concept and you know the condition of your project. If you have indoor project, okay, you have outdoor project, you have different also scenarios. If you have outdoor project also, it depends if it is like normal weather, like here in Middle East or in Europe, for example, they have too much winds. So this is completely different scenario. The U will be different in this case if you have too much wind. Okay, so this is the way.
Yeah.
So guys, look, I want to say something. I give you all details to make it like comprehensive information between your hand. But in reality, believe me, like nobody aware about the chemical information that I give it to you in this presentation. I covered all aspects of chemical treatment that you can find it in all swimming pools. But usually, the designers, even the specialist swimming pool specialists, they are giving only high level specs for the chemical treatment part. Okay, and they are relying on the vendors to provide the suitable like sizing for their project. He just say I'm using ozone with secondary disinfection chlorination. I'm using pH controller with chlorinator. I'm using solid chlorine tablets instead of liquid chlorine and so on. But sizing and the capacity, the calculation details that I showed to you, nobody like most of the people in the market, they are not aware about it. Okay, so when you speak with someone, you have enough information to go deeply with him, to go in debate, and to show him you understand better than him. And this is the point of this course. We need to reach to this limit. So do not think it is like a very complicated closed box system. It is very simple and very easy. Just to know the concept and you will be number one. Okay? Any question? Okay.
Yeah.
Thank you,
We'll
everyone.
read this. Yeah.
Huh?
We'll study this, then we'll
Can
come to know. Yeah.
Yeah, and everyone, I need to tell you the next session. Now we finished the skimmer. The next session, I will explain only the balancing tank because this is the only difference between the overflow and the skimmer. And then I will show you some practice projects, okay, in order to
Yeah.
digest more the information. And we will agree what is the last session, the session after the next session, what to do. Because we are going to do, as we said before, you will do a project presentation. We will divide you like groups, okay?
Yeah.
You will handle some projects, and you will show me. You will present how to design this project. I will show you what to do exactly, okay? And we will agree together what are the steps to be considered in this last session, okay?
Okay. Yeah. Thank you.
Thank you.
Thank you. يلا رمضان كريم.
Ramadan Kareem.
Ramadan Kareem. Yeah.
Hey, Ramadan Kareem. Thank you. Thank you.
Thank you. يلا باي باي.
Bye.
Thank you, Khalid.
Thank you. Thank you.